So you can grab this slide deck from bit.ly/PyBEL2018, and I'll send this one to William so he can collate them all together, and we have a nice slide deck to share with not just people in this room, but anyone else who wants to see all the great stuff that we've all accomplished over the last couple of years. Yeah, so I think my talk will also be very academic, which is kind of a cool breath of fresh air, maybe a little scary compared to all the industrial applications that we've seen going by. So everything's got a little bit of a opinionated slant from the academic side, and this is cool. I think it's neat that we have a little bit of variety going on. So my talk is about the PyBEL ecosystem as of 2018. And the first thing I have to tell you is about some of the technology that I've built and what is PyBEL. So when I started working on Bell was in my master's program in Fraunhofer, which is in Bonn in Germany. And in our group, there's a lot of focus on curation and a little bit of focus on analysis to this point, and we've really grown that analytical side. But the problem we had is we had a lot of Bell script that was written in kind of an amalgam between Bell 1.0, 2.0, and some sort of crazy extensions. So not only did we need to build a new parser, but we also needed to think about how we can take the results from Bell and turn it into a network that we can do network games with and run analyses. So I built PyBEL, which is a pure Python package with very few dependencies, and one of the things that I was really focusing on with all the things that I did is that things had to be easy to install, very easy to understand, and the documentation had to be exquisite. So hold me to it. If you want to read any of the documentation for anything, I've put a link for every single thing that I've done in the top right. You can follow those, and most of the GitHub repositories, they all have links to documentation, links to test suites, all that thing. So PyBEL is a parser and a validator for Bell script 1.0, 2.0, and the weird Fraunhofer Sky variant of it that includes some of the things I hope we can include in a Bell 2.1 standard. I think a lot of us will agree some of these are great ideas. We have to have a graph structure that's built in the Python language that's easy to query and do things with, and I deferred to NetworkX, which is the de facto library in Python for dealing with networks. And immediately an entire suite of network analysis tools becomes available. On top of that, you can then build new tools that are specific to Bell and specific to the application at hand. And the important thing for me was to be able to reuse a lot of things and to build new tools quickly, because a lot of the problems that we solve with Bell are becoming very different from its original intention. And that's awesome, and it's been able to evolve really well this way. So the PyBEL system also has got a very lightweight terminology management and text management system that's also storing nodes, edges, and networks. And so this idea should sound familiar, and it was a good idea, and we all sort of converged on the same thing in the end. So you can think about things almost the same way when it comes to PyBEL versus Bell Bio, and we'll get to some of the differences. The other thing with PyBEL is that it needed to really do a good job converting between formats and making stuff useful outside of the Bell world, because we had a nice conversation at lunch where really what is the limit of our community? What are the limits of other similar communities, like people who are interested in biopacks, SBML? Can we combine efforts? Where is that possible? Where is that not possible? This is something that we have to continue to think about and even discuss across these boundaries that we've set. So what I think is successful about PyBEL, it's beyond just a parser. I think that the problem of making new parsers is basically solved, and it's really focused on mapping the network structure. Now, I won't say exactly what is it doing, because I have documentation on all these things, and I want to get to some of these applications and what problems can we really solve with this. The formats that you can really deal with now, first of all, you can upgrade Bell statements. That's useful. You can store them with this binary format, pickle, which is built in Python. It's also very tightly integrated with the CX format, which underlies the index platform put together by Dexter. And he's, I think, a little sad he can't be here to discuss with us what is the future of index and how do these things work together. But it's really good that we can easily go back and forth between these things. OK. Also, having many different JSON schemas to encode the same sort of network for different applications. The first one I listed is D3. And this is a very simple visualization library, so you can build web applications that do visualization with JavaScript. It's also possible then to import PyBEL graphs into Jupyter notebooks and then share these things with people very quickly. Also, the Cytoscape format, so you can use Cytoscape.js, which is also a very powerful network visualization, and JGIF, so we can maintain compatibility with the other BEL ecosystem resources. Okay, I won't say any more about the integration with Indra, other than we've done it with a lot of cool work put in by me, John, and Ben, and they'll talk about Indra very soon. And they're really the ones who enabled some of these conversions between biopacks, SBML, and some of these other great formats that now we can convert BEL to this. We can take some other resources, convert them to BEL. And in the end, PyBEL is also using a relational database to store a lot of these things, so you can query things in this standard sense. It's using a library in Python called SQL Alchemy, which makes it very easy to reason about dealing with these databases. And you actually don't even have to think about SQL itself. It's using Index also as an interchange system. And you can also use Neo4j. It exports to Neo4j. I haven't put a ton of time into that, but in the future, it's something that also solves some of these scalability problems. And like the ontology lookup service, having multiple parallel databases, this is also an idea that you've used. Each database sort of solves a different problem, but if they're all being maintained together, then you can use the most powerful parts of each. Okay, so this is PyBEL, which gets our BEL script, turns it into something we can write programs about and solve some real problems. So the next thing that I wanted to do once we were able to start getting a data structure inside Python is to get lots of data from lots of different places. And I started playing the game of converting different structured knowledge bases into BEL. And I think the first really good example, which maybe some people are familiar with, is that CTD was converted to BEL. CTD is the chemotoxicogenomics database. It has lots of really interesting relationships describing the functional and molecular impact of chemicals, whether it's increasing, decreasing the expression of RNA or proteins, or actually the susceptibility that compounds have and their relation with the proteins that are sort of changing their activity, and also its effect on methylation patterns, post-translational modification patterns, and some other things. So it's a really rich database, and I think when they started curating this, they also had some of the ideas from BEL in mind. They weren't explicitly using BEL, so making the database downloadable easily and then exportable into BEL is very important. So all of the different repositories that I call bio-to-BEL repositories have a system for downloading and structuring, downloading and parsing the data from their original sources in a completely automated way, and then storing them in a relational database, which is usually appropriate for most of these, which makes it useful for not just BEL applications, but some other things. And then having mappings from these sources to BEL, so we can easily take a given network and we can enrich it with the relevant information, or we can just dump the entire database as BEL and share it. So I've done this with all of these ones that are listed already on the page. There's also this repository. Actually, it's an organization on GitHub that has an entire list of the different sources. I think another useful one would be something like EntreGene, which enables orthologization, and a lot of the equivalence mappings, which PyBEL actually handles a little differently. And I will suggest that we add an equivalence relationship to the BEL language later, because PyBEL strays a little bit from the equivalence system that was in the original BEL framework and encodes those directly as BEL. And I took this inspiration from RDF because I think that works really well for RDF. And this makes it possible to abstract away some of these other resources that are necessary to solve these problems. We can discuss this a little later. So really another one of the things that interested me with bio-to-BEL is to get lots of information about chemical databases. I did my bachelor's in chemistry, and I always wanted to be a chemist doing informatics. And I was a bioinformatician for a while, and now I think I can be a chemoinformatician again. So this is bio-to-BEL. And the next step is, once we have lots of stuff in BEL, what can we do with it? It's time to start building systems that are reusable, that let you work on graphs. So grouping, filtering, summarizing, and then more interesting analysis on your BEL graphs. I decided we had to re-implement some of the algorithms that existed and were published. So we rebuilt reverse causal reasoning. Shout out to Natalie. We implemented some heat diffusion analyses. So one really cool one that I read about is called the HotNet algorithm. and of course the MPA algorithm from PMI from Florian Martin and crew. And then one of the first algorithms that our group published that analyzes Bell networks is the neuro-MMSig enrichment mechanism enrichment algorithm. I'll come back to that in a minute. And we also started getting into the business of checking the biological grammar, which I think I could spend a whole talk talking about this. But it's a lot of different little motif-finding algorithms that find contradictions and some stability things, weird structures within graphs that exist that don't really make sense. Or if they do make sense, then you need to at least contextualize it more. And finding this sort of stuff to present it to curators or to biologists that are interested in knowing what's in my network and motivating them to either curate more or to do some sort of at least exploration around that. Okay, and my image right here is about a time series analysis where we used one of these heap diffusion algorithms, sort of like the HotNet2 algorithm, to analyze a data set from Alzheimer's patients at different stages of the disease. And each of these lines represents the pattern that a biological process takes. So what happens is when you do this, you actually see there's some patterns of things that go up as the people progress through the disease, some things that go down, some things that actually go up in the middle of the disease, which is called mild cognitive impairment, and then go back down for severe Alzheimer's disease, and some things that aren't really perturbed at all. This is what the data says when you can take a differential gene expression experiment cut up by disease stage and use a network that's specific to Alzheimer's disease to make this analysis. So to put together some of this stuff, I'm calling this the Bell query language now, and I think this is something that we can be a little more general about later. Having a way of transforming and combining and doing some sort of things to networks that's reproducible was really important to me as well, not just because I wanted to be able to reproduce my work, but I think some of the ideas that we have in the SQL language and in Sparkle could be useful for Bell networks. And so I'll come back and show the implementation of this and how you can try using it in Bell Commons, which is our visualization system. The steps that you would want to take when dealing with some networks is you pick the networks that you're interested in. This is the functional groups of edges. So for example, you might want to take a network that has to do with Alzheimer's disease, and you might also want to take a network that has to do with Parkinson's disease and combine them all together. Then you might want to select certain parts of that based on the nodes, the neighbors of those nodes, even some annotations. And we call this seeding the network. After you seeded the network, you might want to apply some transformations like adding the central dogma, inferring which RNAs and genes should be attached to proteins or mRNAs. You might want to prune away the non-useful central dogma nodes you've just added because they're not connected to anything else. You might want to delete some nodes. You might want to expand around some other nodes based on the original networks, but you've seeded down to something and you want to add some more. And then later you might want to even select certain kinds of paths from that. That's what this where statement is. This sort of thing is called metapath search, and this was implemented, or this was described in a paper by Daniel Himmelstein a couple of years ago, but it was actually an idea that I came up with on my own, and then I found out someone else had done it already, and I said, this is great, somebody else already used it for something. I'm not crazy. So even something we could do in the future is to have more Sparkle-like queries that allow people to write down what kind of transformations and modifications they want to make to their networks to get to the edges that you really need to use. The idea in the end also is to make sure that you can store these queries either in this sort of language form that I think would be familiar to someone who's written SQL or Sparkle, and then you could also store it in a structured format like JSON, which is how my implementation is using, or what it's using right now. Okay. All of these things are nice. Python programming is great, and everyone around here loves to program, but not everybody is a programmer, and we want to make sure that Bell is accessible to a community of people who aren't comfortable with that. We want to make sure there are tools available for people to do interesting stuff, like I just described. And what we had to do to make that possible is to develop a web interface for all these systems. So Bell Commons first was focusing on providing feedback to the curators in our group. And then it became a little more than that, because once you have all these networks in the same place, you can really start doing interesting things like summarizing them. This is nice for even people who are doing curation as their deliverables for their job. for also doing this assessment of quality, like I said, with the plausibility checks, which are called the biogrammar, and then for fun exploration, because sometimes you just want to know everything you can find out about your favorite protein. So PyBEL Commons makes the functions from PyBEL accessible to the general audience, and then it also gives a front end for doing these analyses that I described in the slide from PyBEL Tools, so you can analyze differential gene expression, and it makes these accessible to people. I think this is really, really important. And as we want to spread and evangelize PyBEL, we need to make sure that the tools that we have are really high-end and smart-looking. And you guys have seen BioData Studio already. We'll have no problem with this in the future. OK. So we built all these technologies, and it wasn't just the purpose for me to build technology. I wanted to really solve some cool problems. And I'm going to present a couple of them quickly, and then we call it a done presentation. So the first one, this isn't my work. This is from Daniel Domingo Fernandez, and he's also been really instrumental in bringing some cool applications to our PyBEL knowledge assemblies. So there's a project at Fraunhofer Sky called Ethionomy, which is part of the IMI project. It's an IMI project, and throughout this project, they built some quite large knowledge assemblies related to Alzheimer's disease, Parkinson's disease, and epilepsy. And Daniel took inspiration from a lot of enrichment algorithms that are about memberships of things within sets, but then took the fact that we have these knowledge assemblies and used the topology of these knowledge assemblies to inform enrichment algorithms even more, and use the directionality of the parts of the knowledge assemblies. So you have these large knowledge assemblies for each of these diseases that have been sliced into dogmatic candidate mechanisms, whether it be insulin signaling or some other things that you would really consider like a pathway if you looked at Reactome or KEGG or Wiki pathways. Then you can apply this algorithm individually to the different mechanisms based on what kind of genes you're interested in, or SNPs that you're interested in, or even these knowledge assemblies contain information about imaging features. Now for PLM crew, this would be interesting to see. This is one way to include some of these other modalities of measurements to connect them to PyBEL, and then allow even some data-driven analysis of a given patient to get a signature. And this is what the word SIG is as part of it. This is the multimodal mechanistic signatures of neurodegenerative disease.
So mechanism here is referred to like a subnetwork or like a regulon?
Yes, the mechanism is a subnetwork in this case of the whole knowledge assembly.
And is it like, so it looks for sort of enriched subnetwork? And does it look?
So you'll give a query, basically a gene set that you want to query, and then it will look for the networks that have been defined as subnetworks, which are corresponding to mechanisms. You also keep in mind that with these neurodegenerative diseases, the mechanisms of disease are not so well defined. So these are candidate mechanisms, things that seem to be grouped together in other fields and would make sense as being grouped together in the neurodegeneration diseases as well.
So the mechanisms are curated by?
Yes. And so the link to this website is right here. And I'll present something else we did with NeuroMSig letter, and we were asked by the reviewer to much better define exactly how the curation procedure works. So you can read exactly how we did it, because I forced Daniel to write it. And it was really a lot of work. It was 5 years of work of curation to put these things together. So we have to, as consumers of PyBEL and enablers of PyBEL, always appreciate what it takes to build these knowledge assemblies. OK. The next application is the Bayesian Viewer, also coming from our colleagues Shashank and Daniel again. The Bayesian Viewer is probably due for a new name. So again, in neurodegeneration, they took the Alzheimer's Disease Neuroimaging Initiative, which is one of the biggest cohorts of people with Alzheimer's disease that they've measured on many different scales. They have genotyping information, they have differential gene expression experiments that they've done, and they have imaging studies. And what they did is they took this cohort of people, which I think is some number of hundreds of patients, and they did some cool machine learning. They developed a risk model to pick the best features out of this quite large set. I mean, if you think of all the SNPs that they measured, all of the genes, and then all the neuroimaging features, this is in the tens of thousands of features. So they developed a risk model of the most important features, and then they took those features and used them to build a Bayesian model of the conditional probabilities of one thing affecting another. Now, the Bayesian network is a very cool way of distilling a very complicated data set down into understanding the relations between the features themselves. The cool thing is a lot of these features are also mappable to Bell networks. So they took the results from this Bayesian modeling, mapped it to the Bell networks that are relevant, and provided yet another way to explore and analyze and interpret the results from Bayesian modeling on a given clinical data set. So as this is going forward, you can do lots of other cool things to model clinical data sets in a Bayesian way. So the next step is to do a longitudinal model of the ADNI data set, to bring in some other data sets from Alzheimer's disease cohorts that are independent, see if you get the same results, do a validation, and to also do the same thing with some other famous Parkinson's disease cohorts, such as the PPMI, which is the Parkinson's Disease Progression Marker Initiative. Okay. So this example is showing that inside you have the dependencies between NK cytotoxicity and the complement and coagulation cascade. And when you see this edge that shows these are two pathways that are causally related, so inferred causation from Bayesian, not experimentally validated, you can bring up the networks that are relevant to those pathways, and then you can explore on the right. Okay. The next project we're working on has to do with making Bell quantitative. And this is the problem that we thought about before, and there's a lot of different ways to go about solving it. So this is what I've come up with. It's possible to get lots of interesting quantitative information from different sources, and we'll focus on chemical information. How does a given molecule, let's say small molecule, inhibit a protein? How does it bind to a receptor or agonize or antagonize it? This would be very interesting to the pharmacologists in the room. And if we have that kind of information, what do we do with it? How do we make it play nice with Bell? With PyBEL, it's as easy as storing it as a property of one of the edges. In general, you can match up a given edge to quantitative data as well. So it's not so specific to PyBEL solving this problem. So what can you do once you have quantitative information with Bell? When it comes to having inhibitors or receptor binders, you can start playing fun games in chemoinformatics, which, like I said, this is what I always wanted. And we're going even one step further than what chemoinformaticians do, because we can connect our drugs to our targets, but targets are also connected to their functional consequences inside Bell. And now we don't just play the game of finding out what's the best chemical for this target, but what's the best chemical for this set of targets or the set of this mechanism, the downstream effects that this chemical might have. And when we have quantitative information, we can make comparisons and we can make rankings. And in the project that I'm now tasked with to finish my PhD, the Human Brain Pharmacome, we do this combined with drug repurposing strategy, and we have partners in Hamburg that are the screening platform and a different Fraunhofer Institute. They're going to test the results that we have as we make proposals of drug repurposing candidates that we want to see. Which ones do we think will have an effect on a given mechanism from MMSig? We happen to be interested in the results or the downstream effects of the tau protein in Alzheimer's, which very quickly is relevant to these tangles that show up that you see in Alzheimer's patients' brains after they've been cut up, after they've passed away. So this is one thing that's going forwards, and I don't have a lot of material for you on this right now because it's happening right now, and that's what I'll go back to at the end of the week and continue working on. Okay, the last thing is EpiCom, which was the example where we started to try and use NeuroMMSig to interrogate these mechanisms based on the targets of given drugs. And what we did is we found a drug, carbamazepine, which has been used for epilepsy patients, but it also has been shown to have therapeutic effects in improving cognition in Alzheimer's disease patients. So we have this idea that this drug has some effects on both Alzheimer's disease and epilepsy, but we don't exactly know how. The thing that we did is we found all of the targets that were annotated to this from DrugBank, from PharmGKB, some of these other databases that are in nice structures and we can get programmatically. And we queried NeuroMMSig with those gene sets to figure out, are there any mechanisms that overlap? And it turns out that there are. The most prominent one would be the GABA receptor signaling and the downstream effects of that. So I've made a little cartoon here of the effect, and let's not focus on exactly the different parts of it. But the idea is that you can now use one of these algorithms to gain some insight. And the next step for this one is we've done this really in detail for one drug, but we can now programmatically access basically all of drug bank, and then why not do this for every drug against not just Alzheimer's epilepsy mechanisms, but also we have Parkinson's mechanisms. So we can find any other mechanisms that are overlapping based on a given drug treatment. And you can use this to propose repurposing, for one, or to gain insight into which mechanisms really are relevant for the disease. Okay. With that, I think I conclude. Does anyone have any questions about any of those? I did a smattering of different things. So again, all the slides are going to be available, so you can follow any of those links on stuff that sounded interesting. Yeah?
So the PyBEL comment? No, the Bio2Bel.
Okay, Bio2Bel, yes.
Yeah. You're producing Bell scripts? Is it Bell 1, Bell 2?
So PyBEL will canonicalize any Bell graph into a Bell script, or it can go into anything. When I make Bio2Bel, I actually just build these Bell graphs in memory, and then you can use any of the import or export features to canonicalize it to whatever format you want. So for you, I mean, what you'll have to do at some point is write a PyBEL to BioDaddy exporter, so you can take advantage of things that exist already and not recreate them yourself.
Yeah, that would be great. As much as we can collaborate, that would be awesome.
Might as well not solve the same problem on our own.
Yeah.
And I think also John and Ben will benefit from these things too.
And in this, so most of these data sources don't produce statements, I would imagine, right? Like HTML, we're going to produce statements.
I may have glossed over a little bit. So Bio2Bel, one, it's rewriting of these namespace generators, and also two, it's when applicable, taking statements. HTML actually has lots of information about equivalencies and orthologies, and so that's useful. Even though those aren't really mechanistic statements, it definitely helps contextualize information. And if you have this pipeline builder later, you can say, take my graph, enrich it with all the HGNC orthologies, and then collapse these orthologies. I want it to look like human genes in the end, or I want it to look like mouse genes in the end. And then you can run your analysis. For example, in Alzheimer's, I throw away all the mouse genes because I don't personally believe Alzheimer's is very well modeled in mice. I think people are arguing about this a lot. But in some other diseases, you have the appropriate model organism, and then it's fine. You can combine these things together and really make use of a lot of different types of literature.
And that's something that maybe the three of us can talk about offline. I store the equivalences and orthologies in kind of a separate section.
Yeah. Whereas the Bell language already has a statement for orthology relationships. It doesn't have the equivalence one. This is one of the weird variants I added to PyBEL, and so this is good why we're all here together, and we can decide which ones of these are really the best. Is it possible to continue doing things differently but still have kind of a concept? Yeah. Anything else? Okay, thank you.
Good work.